Hi, the section 13.4, the deviance. So this gives the hypothesis test, the more accurate hypothesis test for logistic regression. So it corresponds to ANOVA for linear regression. So ANOVA uses basically F-test. So linear regression is good. And if you want to compare the null hypothesis against alternative, usually the smaller model against larger model, we have the exact statistic, the F statistic, and you can use the statistic to calculate to test the hypothesis. And for logistic regression, basically we have to rely on the likelihood function. So basically, the log likelihood. So if we have the two models, smaller and larger, and we compare the likelihood, then we have some asymptotic theory that when we should reject the null hypothesis, when the larger model is significantly better than the smaller model. So deviance is basically the function of the likelihood. So deviance is actually the negative 2 times log likelihood minus some constant term. So the constant term is actually the negative 2 times the log likelihood of the best model. So best model means basically the model which can predict all cases perfectly. For example, if we have 100 observations, if we have 100 parameters, we can explain everything. So that is the meaning of the best model. Okay, so the deviance is, to be exact, defined by the 2 times the summation of this. But actually the principle is discussed as the top line. So D is basically negative 2 times log likelihood. So if you go back to the definition of log likelihood, then you can see that this is the solution. Yeah, so we don't go into the details of the definition, but basically the D is based on log likelihood function, and it can be used for testing. And actually this D, follows the chi-square, the n minus p minus 1, if this model is sufficient to explain the response variable. So if the D becomes larger, actually the fit is bad. And if D is equal to 0, the model is perfect. So larger D, then we should reject null hypothesis that the model is correct. And then we have the asymptotic result, statistical result, theoretical result that the D follows the chi-square distribution with degrees of freedom n minus p minus 1. So that means if we have the 2 predictors in the model, then chi-square of n minus 3. The 2 predictors means the 2 predictors plus intercept, so n minus 3. So if the sample size is 100, the chi-square of 97. And chi-square distribution is the skewed distribution. With larger degrees of freedom, its approaches to a kind of normal distribution, but still we have the heavy-tailed distribution. So like this, and we reject our model against the beta model if D exceeds some threshold, maybe 95 percentile of this distribution. So this is rejection region. So large D, we reject our model for a beta model. And the deviance can be also used to compare 2 models. So the previous page that we calculate if we test if our model is sufficient to explain the situation. So we think about the perfect model and our model is not significantly worse than the full model, then perfect model, then our model is okay. So next one is comparing 2 models, the smaller model and larger model. Then you can calculate this deviance for both models and the deviance of model 1 and deviance of model 2. And the deviance of model 1 is larger. So because the model 1 is smaller model, so smaller likelihood, so that is the larger negative 2 times log likelihood. So this is always larger. And D2 is always smaller. So at least this is positive. But if difference is too large, that means the model 2 is better than 1. So the negative log likelihood is the value that the smaller is better. So a kind of the error size, it's similar to error size. So if the error size is too different, then we should choose the model 2. If error size is similar, then probably that we should not reject model 1. So we can accept model 1. And actually the D1 minus D2 follows chi-square distribution with degrees of freedom Q. And here Q is the number of the difference in the number of degrees of freedom. So in this case, the model 2, we have seen that the J can be B or C. Okay, so to be exact, this model is Y is equal to mu plus the alpha I times the indicator function of Y plus beta, sorry, the alpha Y, beta B times indicator function of B, and beta C times indicator function of C. So we have the two additional parameters here. So Q is equal to 2. Or you can say that the model 2 have 3 parameters and model 1 has 1 parameter. So Q is equal to 2, the difference. Yeah, so if D1 minus D2 is larger than the some threshold value of chi-square distribution, so that means that we have chi-square distribution with degrees of freedom Q, then we have this. And if the D1 minus D2 falls in the range larger than this threshold value of chi-square 0.95 of Q, then we should reject null hypothesis and we should reject model 1 to support model 2. And actually that can be done by this ANOVA function, but the meaning is different from linear model. So the GLM, and we have to put the test is equal to chi-square. If we don't put it, I think the some columns, so this column is not generated. Okay, so here's deviance, null deviance, the deviance. So this is the D1, and this is D2. So the difference is 20.74. And this follows chi-square distribution with DF2 because this difference in degrees of freedom is 2. Yeah, so to be exact, we have the 6 observations in total, right? So we have the 6 lines. So the X1 have 2 parameters, so 6 minus 2, so 4. X2 have 3 parameters, so 6 minus 3. And then the intercept, so the 2. So we have the difference of 2. So this follows chi-square 2. And actually the 20 is pretty large number. So chi-square distribution with DF2. In general, chi-square distribution with the DFK, expectation is K. So if the value is much larger than K, so that is really large value. And actually the P value is very small. So that we reject the smaller model. Yeah. And actually, if we change the order of X1 and X2, the result becomes different. Yeah, because this is sequential model. So we compare, basically, the probability is equal to X1. We compare this, excuse me, against pi is X1 plus X2. So we compare these two models. But here, the next table, we compare y or pi on x2 and pi on x1 plus x2. So we test between these two hypotheses. So meaning is different. So actually this time the D1 is equal to this and D2 is equal to this. So the difference is here. And the difference in degrees of freedom is 1 because we add x1 term and x1 is just 1 term. only the alpha 1 term, alpha sub y term. And df is 1 and the difference is 2.24. So it's a kind of in a gray zone. So the expectation of chi-square 1 is 1. So 2.24 is certainly larger than that, but not much larger. And the p-value is actually 0.13423. So it's not significantly better. So including, so this model, so pi on x1 plus x2 is not significantly better than pi on x2. So if we have information of x2, x1 does not matter. So that is the result here. And to get p-value, that we can explain with graph, but you can use the chi-square function and the chi-square, the probability function of chi-square, and we calculate the the upper probability. So once you observe test statistic, your test statistic is here. Then you calculate this probability. So we have to put the 1 minus here. Yeah, and other things that you can use in the same way. Yeah, so the conclusion is here. So x2 is highly significant in any results. So that has been observed in the tables. And the x1 is marginally significant with p-value 0.0627 if x2 is not in the model. So if no information is available, then if we get the information of x1, it may be useful. It's marginal. The p-value is around 0.05. And x1 is not significant if x2 has already been in the model. So if we have information of x2, x1 doesn't add much more information. So that is the result from this test by Deviance.